Hello, my name's Alec Glover. I scaled a GPU cloud from 0 GPUs to 1,000 GPUs, hand building GPU servers, all from scratch. Today, I'm going to show you exactly how we built those servers and how we put it all together to create a GPU cloud that functioned stably and with a ton of performance at a really low cost in a warehouse. The plan is, I want to take you through all of the different technical decisions that you're going to make building your GPU servers and how will those components fit together and ultimately influence the overall outcome and performance that you're going to get out of your GPU cluster. So this is actually going to be the first of a 6-part series that I'm doing about how to build a GPU cloud. So if that's interesting for you, please subscribe because these videos are going to come out over time. And if you haven't watched my intro video yet that covers all of the 6 topics, I'll put it right here or something, and I encourage you to check that out because it's only 20 minutes long and it's going to show you sort of the overall picture, whereas this video is going to be very specific to exactly how are you going to build a GPU server and sort of the technical details behind that. So starting with GPU selection, you're going to want to pick the GPU that obviously fits your needs. So if you're doing a business where you're renting GPUs to people, the market typically loves the newest thing out there. And that's true, obviously, when the market's really pumping and everything's rented, you're able to get a huge hourly rate for, right now, something like a B200. And then when the market pulls back and people stop renting things, people typically like to have the best, and it's the lower end stuff that is typically just going unused when the market is slow. So I would encourage anybody who's doing this to run his business, who's trying to rent these out and make money, always look to the newest generation. It's going to trade at a bit of a premium, but it's going to have a much more friendly depreciation, and the longevity that you're going to have in the rental market with it is going to be a lot better. That's sort of, I guess the business decision you need to make. Assuming you're consuming it, like you probably know what you need. What this is going to do is, depending on the GPUs you pick, that's going to influence, I guess, whether you build it, whether you buy it, and, what are the form factors, right? So if you go the consumer GPU route, and you're doing something like a 5090 server, 5090s are obviously a consumer graphics card. They come in a form factor that's like intentionally a pain in the ass to put in a server, like the one behind me. That's obviously all, because it's never meant to go in a server, and they go out of their way to make it so that it doesn't work very well. A enterprise card, or something that is meant to go in a server, or, is sort of a hybrid like workstation server card, they'll have a, specific form factor. They call it full height, double width, meaning it's 2 PCIe slots long, and full height meaning it takes, a full height PCIe slot. And typically those are, full length as well. That's a standardized form factor that will work in a server, and you can get those GPUs as either, actively cooled or passively cooled. So let's take the RTX Pro 6000 is a new GPU that's come out. It's like a 5090, but has 96 gigs of VRAM. That GPU comes in an actively cooled variant, which you could put in a chassis that doesn't have airflow coming through it. Or you could get the passively cooled variant, which needs to go in a server chassis with, really, really high fan pressure over the GPUs, because the only thing removing air is the GPU, or the fans from the chassis. So there's the passively cooled ones, there's the actively cooled ones, and then there's a consumer grade special form factor ones. And the consumer grade GPUs are not only taller than full height PCIe, but they consume anywhere from 2.5 to 4.5 PCIe slots in width. And then on top of that, you want a bigger buffer, because the way that the fins on the heatsink are facing, they're not blow through. So when the fans hit those GPUs, it's like hitting a wall. And because of that, you actually need a lot of space around the GPU for the GPU to exhaust the heat, and then for the server chassis fans to actually pick that heat up and push it out. So that's why there's such a monster chassis behind me. We were running 3090s, 4090s, and 5090s. We ran a mix of 10U chassis like that one, as well as 7U chassis. And we got all of our custom chassis from a company called One Chassis. I know it's something people keep asking me. I think it costs anywhere from $1,500 to $2,000 for each of these chassis, which sounds expensive, but there's no real alternative to it, right? Like if you're going to do a GPU cloud with, let's say, more than 100 GPUs, you just end up with all of the problems of a data center. And if you can't start to conform to how data centers are supposed to contain heat and distribute power, you just run into scalability issues. So I would say to anybody who's looking to do this and looking for something scalable, just go for the chassis immediately. Like it's the only way to grow beyond a certain point. So that's GPU selection. The next piece that's obviously influenced by this is the PCIe generation. PCIe is going to be like, in this day and age, you're talking about either PCIe Gen 4 or PCIe Gen 5. And remember that a single lane of PCIe Gen 4 can move 2 gigabytes of data per second, like bidirectionally. And the same is true for PCIe Gen 5. It's double that. So it's 4 gigabytes per second per lane. So let's talk about, all of these GPUs demand a x16 slot, meaning like a 5090 theoretically has 64 gigabytes per second of bandwidth coming in and out of it, or that's what it's capable of. And then for something like a 4090, you're talking 32 gigabytes per second. In practice, I've seen it be more like 24 and 48 is sort of like what the actuals end up being, but there's obviously a lot more than just like the theoretical bus bandwidth going on there. Right now, building for inference, let's say, you're going to want to look at, I guess, the cost savings that you could have if you go and put a PCIe Gen 5 card on a PCIe Gen 4 system. And that's largely driven by memory, actually. So a PCIe Gen 4 system is using DDR4 memory in most cases. And that essentially allows you to save a huge amount of money on the stuff that goes around the GPUs. And you can imagine if you're using something like a 5090 or something maybe even more low end than that, you don't want to be spending tens of thousands of dollars on your memory to support that. Because the cards are, obviously like they only have so much VRAM in them, the bus bandwidth moving data in and out of them isn't so important. Whereas, say you've got a 6000 Pro or RTX Pro 6000 GPU that has 96 gigs of VRAM, there's just like more space for you to move data in and out. So you'll actually benefit from that extra bandwidth. Whereas, like a 5090, you're talking about 32 gigs of bandwidth, and PCIe Gen 4 can move 24 gigabytes per second of data. It's obviously more complicated than that. If you have, very, very high memory transaction workload, it might make sense for you to just go for the PCIe Gen 5, but I can speak from experience, like when we were renting the 5090s out to our inference customer, they actually didn't care that it was on PCIe Gen 4. Definitely something to consider, especially if it can save you $10,000 on every server you build. The next thing to consider is, so around the PCIe selection, if you go with a PCIe Gen 4 setup, you're going to be using SlimSAS risers. They look like this right here. So this is a SlimSAS cable. Essentially what this is a cabled 8 lanes of PCIe Gen 4. This will obviously connect to a SlimSAS port, which can either be directly on your motherboard with a motherboard like this. So this ASRock motherboard obviously doesn't have any PCIe slots. It just uses SlimSAS cables. And you basically, what you do is in the BIOS, there's going to be a setting that allows you to take 2 ports and either treat them as an X16, so you merge them into a single port essentially, or you can treat them as independent 8X ports. This board has 19 SlimSAS ports on it, meaning that you can connect 8 GPUs at full X16 bandwidth to that motherboard, which is incredible, obviously, because that's a ton of PCIe bandwidth. Or what you could do is you could run them at 8X bandwidth, and then you have a lot of PCIe left over to use for stuff like storage or for NICs, or maybe just more GPUs. There's a limitation with that motherboard that you're not going to be able to connect more than 14 GPUs to it. In any case, there's no clean way to really build a system with 14 GPUs, unless it's on a shelf or something. That's the motherboards. If you don't go that route, there's these that exist. So a lot of people send examples of really cheap, slot-based PCIe motherboards, and it works. You can get these adapters that basically convert that slot into SlimSAS cables, and then you cable the riser to it. And then this lets you get 8 GPUs organized in, a relatively small space, right? You plug this into your motherboard, and then you've got your GPU over here, and you can spread it all out as needed. The downside of these is that you can see this one, it doesn't have anything like any circuitry on it, increasing the signal integrity coming off of it. So this conversion here from like a slot-based PCIe signal, basically going as a trace and then funneled into a cable here, you're losing a lot of integrity across this. And so what I've been told and I've also experienced firsthand is you end up with a ton of PCIe errors on your bus. And so for a card, it racks these up over time, and eventually if it can't correct the errors of the data transmission that it's getting, it'll crash. And this is a super damaging crash where your entire driver basically dies and you have to reboot the machine. So we were doing this originally, we were buying these cheap motherboards, we had these like converter cables or these converter adapters, and then, it would work fine for a week, a couple weeks, whatever, and then you'd get the crash, and then you'd have to reboot the machine, and then whoever was renting that machine, like reliability and stability is measured in hours per year. Like a reboot due to a crash like this it happens. Customers are used to seeing it, but it's very damaging when it does, and so it's hard to run sort of a stable customer base because you'll lose a lot of customers if you keep losing GPUs like that. There's such thing as versions of these that do have what's called a redriver on them. And what that does is it reads the signal off of the slot, and then that is processed in some circuitry that boosts that signal before it puts it back through the cables. And so that adds a lot of stability to a system like that, but it increases the cost of these risers like a ton. Like you're talking about, it's going to be more than $100 per riser, which means that, the money that you're saving on that cheaper motherboard, you're just going to be spending on technology that you need to put in the slots of it. So the conclusion that we came to after a lot of fighting this is that you just need to buy a motherboard that has the SlimSAS ports on it. Okay. And there's the ASRock boards that I've talked about a whole bunch. There's a single slot version, so put the name here, and a double slot version here. You can buy them sort of piecemeal on eBay. ASRock will only sell it to you in bulk, but then there's sort of a reseller community around it that they'll help you get orders, or they'll aggregate, orders where you can get 5 or 10 of them or whatever. So that's PCIe Gen 4. PCIe Gen 5 works in the same way. It just works over something called MCIO. So those risers it's the exact same concept. It's a powered riser. It's got, 2 X8 cables coming into it. In their MCIO cables. And the same holds true. You can get things that can adapt a normal motherboard and turn it into MCIO ports, or ASRock has single socket and dual socket MCIO boards that let you get, MCIO directly off of the motherboard, which that's hugely valuable, obviously, because then you can just get your X8 or X16, PCIe Gen 5 straight to your GPUs without needing all this extra hardware in between that, is prone to failing. I guess the warning around that is that as PCIe speeds increase, so like the jump from PCIe Gen 4 to Gen 5, that signal integrity is a lot more finicky. For us, the first PCIe Gen 5 risers we tried, I bought them from 10G Tech. They were cheap and they were incapable of running a GPU at PCIe Gen 5. Like, I'm not even kidding. You could run the system for half an hour and then one GPU would fall off the bus due to the errors accumulating, and you'd have to reboot the system. So it actually was completely unusable in PCIe Gen 5. What we were able to do is step that hardware down to PCIe Gen 4 on MCIO, and that made it stable. But if you're going to do proper PCIe Gen 5, you need to be very careful about the riser selection. So I've been a longtime fan of C-Pane risers. I think I've responded to a couple comments about C-Pane risers. They are expensive, but you definitely get what you pay for. And I've had the experience with, the guy's name's Christian. If something's not working, he's there and he helps you, figure out how to make it stable. He's got really good advice around that kind of thing. They are expensive though. So the other risers that we've tried and have worked, I actually bought from One Chassis. They aren't a pluggable riser. The cables are essentially soldered right onto the riser, the device riser component, and then that turns into an MCIO cable that you would then plug into your motherboard. Those two risers both work stably at PCIe Gen 5. I know the cable assembly that we were using was $80 an assembly or something like that. I think C-Pane risers, like you're paying, with the cables and the riser, like well over $100 per GPU for it. Definitely something to consider. PCIe Gen 5 is always going to be more expensive than PCIe Gen 4, but it is twice the throughput. So if your workload or the customers you're going after can benefit from that, it might be worth going for. That is if you're going to connect the GPUs to the motherboard directly. So that's like CPUs provide PCIe lanes. Those PCIe lanes are then attached to the device. The other way of doing this is with PCIe switching. So you'll see this with OEMs and their barebone chassis or even just like, you buy a GPU server from a certain SuperMicro, ASRock, wherever it is, and they might introduce PCIe switching into the setup where the CPUs might only have 16, 32 lanes connected to this PCIe switch, and then all of the GPUs are connected to a PCIe switchboard. And what this does is it obviously reserves a lot of PCIe capacity for the host. So you can have a lot of NICs, you can have a lot of NVMe drives, but then it also just puts all of those GPUs on one sort of communication bus that doesn't need the CPU or the motherboard involved. That basically lets you have like a very, very strong signal integrity on that switch and on that backplane that will go in the chassis, but it adds a ton of cost. This is why when you go shopping for GPU servers, it's like, well, why is this barebones chassis like $6,000, and then I'm doing the math and like I can kind of cobble this together for $4,000 another way. And it's because there might be a $1,500 PCIe switchboard actually in that chassis. Definitely something to consider. It's good to just understand that exists. That's how you get more PCIe connectivity onto a host. Like if you look at the spec for Intel CPUs, they only have like 80 lanes of PCIe on them. So when you put two of them in a host, you need lanes to basically interconnect the CPUs. You need lanes for NICs, you need lanes for storage. And then you go looking for GPUs, and it's just hard to find the capacity available to have 8 GPUs all at x16. So that's when they introduced the PCIe switch, and it basically just alleviates that so that the CPU doesn't need to dedicate as many lanes to it. So around the motherboards, I strongly recommend you get either SlimSAS or MCIO ports directly on your board. And I'm going to just rapid fire them all in a big list, like right here. I have seen other boards, like people always ask about like the SuperMicro H12 SSL. It's like super cheap, PCIe Gen 4. It's got a lot of PCIe slots on it. I don't think it's worth it to try to do that and then buy the redriver cards to then turn it into SlimSAS to then cable it around. Like just go and get a board that is designed for this in the first place. We'll end the motherboard part there. But yeah, if you have questions about like certain motherboards or, you want opinions on it, like let me know. I'm pretty strong in my opinion that, you should just get the SlimSAS based ones. The storage, okay? So the way that any server works is you're going to have basically connectivity from the motherboard to a storage backplane. And so in the case of NVMe, every NVMe drive needs 4 PCIe lanes. Like this would be handled through SlimSAS to most NVMe backplanes. Sometimes it's handled through like a 4x connection. Sometimes it's handled through a 32x connection. For the purposes of what you guys are going to be doing, you need a U.2 backplane that will accept a SlimSAS SFF 8654 cable. That's like the exact version of this. And that's going to be 8 lanes of PCIe Gen 4. So for every one of these cables that you plug into the backplane, that'll service 2 NVMe drives. In the BIOS of the system on your motherboard, you're going to want to, make that port in X4. And that's how you're going to scale up your NVMe storage. M.2s are typically directly on the motherboard. They also consume PCIe, but that's just, either off of like a chipset or it's just sort of in the budget and cabled directly to the CPUs. For SAS and SATA, because those protocols are obviously slower and kind of a higher level protocol than PCIe, you can have a lot more of them. I know on those ASRock boards, some of those ports can turn their SlimSAS cables into speaking like the SATA protocol, and you can add like 30 drives on a single one of these SlimSAS ports. If your goal is to have say you're building like a storage server, and your goal is to scale up storage, just devices, like you just want to do hard drives, you're not going to need so much connectivity as if you were to do like NVMe or GPU or something like that. Those are very, very high bandwidth devices, and they just need the dedicated PCIe bandwidth. So that's how that works. You're going to be using backplanes. I don't know if there's that many off the shelf like SATA or NVMe backplanes, but back to one chassis, like part of designing the chassis, we ended up opting for, we put 4 U.2 drives in every server. So super simple drive caddy. At the back, like where this plugs in, there's a U.2 interface. So we would just screw the drive to this caddy, and we'd be able to slide 4 of those into the server, and we'd have those lanes and like those SlimSAS ports set to X4, X4, X4. It just made it really simple where we'd have like a status light for the drives on here. We could easily take them out and change them if they failed. We had the ability to have 4 of them, so we put those in like a redundant array, and if one fails, it's fine, you just take it out and replace it. That's typically how, like most data centers operate. There's so many varying levels of redundancy when it comes to storage that you need to understand, I guess, like what the use case is. If it's for like actually storing long-term data, or it's like super critical data, you typically are going to do that on a network attached storage. Like you're not going to use your GPU cluster for that ultra redundant storage. And that's kind of back to that, like sometimes the GPU crashes and you have to reboot it. Like you can't have that node as part of, the primary storage cluster. What that storage in the GPU node is really good for is scratch space. And so, a lot of people just do a RAID 0 directly on the node, or say you have 10 of those nodes all working together. You could do like a sort of a software defined storage between all of them. And especially if you have like 100 or 200 gig interconnects on them, you can make a very fast software defined storage between your GPU nodes. But that's meant to be fast, not necessarily like redundant and long term. So class of storage is really important when you're designing something like this. And it probably just means that like there'll be systems outside of your GPU cluster that act as like management and storage nodes, where you're managing, file systems and block storage that you're then attaching to the cluster as needed. I won't go too deep there because obviously like that is a whole other realm of complexity. But in terms of building the nodes, you just understand that the NVMe drives that you're going to want to connect to them, that connectivity also comes from SlimSAS. Network connectivity. On the motherboards themselves, you're going to have 3 Ethernet ports, like RJ45 ports already built in. One of them is going to be what's called an IPMI or a BMC port. That is what is going to basically connect to just any management network and provide you an interface for remotely managing the server. This means like a remote viewer where you can see what's going on like on the system. Like as you boot it up, you can enter the BIOS remotely and just watch that happen like from a browser. There's monitoring and alerting on different components within the chassis. So the BMC is like the out-of-band management control plane. So that's going to be one of the 1 gig ports on the chassis. The other 2 ports are going to be, you call it LAN on motherboard. So in the case of the PCIe Gen 4 server, you've got 2 10 gig RJ45 ports, and these are just meant to be network ports that you're actually provisioning in the operating system. So for our case, we didn't need more than 10 gig interconnects. And so we just did like, super cheap Arista switches that were 10 gig, 48 port, and we'd interconnect everything on those ports. So our PXE ran over this, which allowed us to install the operating systems at, 10 gigabit per second. We'd have our, once the OS was provisioned, we would create a bond between the 2 ports, and we'd be able to essentially like, load balance traffic over that bond and connect to the internet at 10 gigabit per second. We could connect to other machines at 10 gigabit per second. And so very, very useful. I know the PCIe Gen 5 variant of the board only uses 1 gig ports, which kind of forces you into adding a NIC to the setup. On the very high end, you could be going for 100 or 200 gig NICs, and then you've got really, really fast interconnection between the nodes. Typically, you would treat a network like that as a east-west traffic. That would be for a storage network between all of the servers, or for GPUs to share data between nodes. You wouldn't really like that. That's not necessarily something that you would implement to move data like out of the cluster to the internet, or like to another part of the data center. For that, we would just add a simple 10 gig NIC in. So this server here, you can see it's got a 10 gig SFP based NIC. This was because the data center that this was in didn't have RJ45 ports for us. So we had to move everything into like an optical network. And so just like super simple, doesn't need a lot of bandwidth, like that operates at PCIe Gen 3 or something, and it's like only a couple lanes, but we did need to add that in. And so that did consume, a riser just like this. It did consume SlimSAS ports on the board, but it's all kind of part of the budgeting, right? Like you have 19 available on the ASRock board, 16 are going to go to your GPUs, and then you've got 3 for storage and NICs, depending on, how far do you need to go with either of those things. That's the network. The critical piece that you want to make sure you have, depending on the board you choose, is something called PXE, PXE. This is going to allow you to remotely install an operating system on the GPU server. If you don't have that and your plan is to run around with a USB stick, you are going to run into some serious scaling challenges. So any cloud software that you put in here is going to rely on, or at least any bare metal cloud software you put in here is going to rely on you being able to very effectively provision an OS to these systems, and then wipe the systems and reprovision an OS when you want to. The alternative to that is that you do like a virtual machine based cloud where the OS gets installed one time and then virtual machines are provisioned and deprovisioned on the systems itself. But I would just strongly recommend do bare metal, get a bare metal provisioning system into your data center. And every time you build one of these, you pick it up, you rack it, you plug it in, PXE boot it, PXE boot your test onto it. Like all of the things that you're going to need to do, you do not want to be manual processes that can be screwed up, because it's fine if you have to do 10 of them, like it might take hours, but over the course of time, if you have to do thousands of operations like this and it requires you to be on site with a USB, it ends up adding up and becoming a huge burden. So that's the last thing I have to say about network connectivity. Power is interesting. So if you're going for like 4090s, we got away with doing 4 1600 watt power supplies all in a redundant setup. And so basically the math that you want to do is you never want to tax any power infrastructure, steady state beyond 80% of its capability. Like obviously it's okay to burst up sometimes, but when you're doing your math, you don't want it to be like, okay, we're going to run all of these power supplies at 100%. We're going to run the PDUs at 100%, the UPS at 100%. Like you just want everything to be at a consistent 80% load. And that's where you're going to find the best efficiencies and the best longevities. So for the math for a 4090 server is you need about 4.6 kilowatts to run it. And I think that the math there was just TDP of the GPUs plus 1,000 watts. And so by having 4 1600 watt PSUs, you're at 6.4 kilowatts available. That was sort of like a healthy enough margin that we were like, okay, if we're running, we're typically well below that 80% threshold. If we were to lose a PSU, chances are we can just continue operating on 3 PSUs, so we have redundancy, and all things are good. The math changed with 5090s because the 5090s, we ended up needing just under 6 kilowatts for the full 8X server. Like the CPUs take more power, the RAM takes more power, the GPUs take more power, like everything was just like scaled up. And, with 6.4 kilowatts of capacity and almost 6 kilowatts of IT load, it was just like, eventually something would fail and the redundancy was very bad. If we lost a PSU, we were like well below the required power that we could need at a moment's notice. So we ended up going with 5 PSUs in each of the 5090 servers, which that sort of creates like an upstream consideration that you need where like ideally you want 5 separate PDUs feeding that, where every power supply is coming from a different PDU, and you just sort of bubble up that redundancy where if any one thing were to fail at any point, like it doesn't put anything at risk. Like you always have the ability to lose something. For anyone who's curious, like the PDB was a huge improvement. Obviously it gave us redundant power and it allowed us to combine the power of multiple power supplies. And then you've got the ability to hot swap anything if it fails. And then off of the PDB, the cables that we're using, we were able to get cables that like would plug directly into the 4090s. So anyone who's seen a 4090 or a 5090 knows like they have that special power connector that if you're just using normal 8-pin PCIe power cables, like you need a ton of those. And if you put 8 of those or 8 cards in a single chassis, like, you're talking about like what, like 32 PCIe 8X, like, or 8-pin power cables. It would be too much copper and just shit in the chassis. Like, there would be no airflow. So these PDBs, they have, the PCIe Gen 5 power connector directly, plug those directly into the GPUs, and it just let us obviously clean things up a ton. The PDB is also going to have all the connectors for the motherboard. So for something like the ASRock PCIe Gen 5 motherboards, there is special power connectors. So you've got to work with the chassis manufacturer to ensure that, you're getting a compatible power delivery system for the motherboard you're using. So that's how the power in the chassis work. What I'll do is I want to show a build basically for PCIe Gen 4, dual socket, single socket, and then PCIe Gen 5, dual socket and single socket. So the first build that I'm going to show you is this is the dual socket with the ASRock motherboard. This would be, the reason to go with the dual socket would be if you want to get PCIe X16 to each of the GPUs. It's that, as well as you're going to have more memory available to basically put on the board. So the dual socket is just like a scaled up version. There's benefits though. So the single socket build would be if you don't really care about the bandwidth going to the GPUs. That's true for any kind of inference workload. And the ability to have all the GPUs on a single CPU means that there's no latency. Basically, if a GPU is connected to one of the CPUs, it doesn't need to jump and like go through that bridge to the other CPU and incur a ton of latency if it needs to interact with a device connected on that side of the PCIe complex. There is advantages to single socket builds, including they're cheaper. You don't necessarily need as much memory either to fill all of the memory channels on the board. So that's a good point. Memory channels, basically for the current gen AMD processors, you're looking at 12 memory channels per CPU, which means that you need 12 DIMMs to fully saturate the memory performance of every CPU. It doesn't matter how big they are, but if you were to put, let's say, 8 DIMMs in, single socket PCIe Gen 5 motherboard, that is basically, or that would be a AMD-based motherboard. That would mean that you're not going to get the full memory bandwidth that those CPUs are capable of. It's quite important that you obviously fill all of the memory channels available. It's not the end of the world if you don't. It's just a performance hit if it's not actually fully populated. On to the PCIe Gen 5 builds. This would be the dual socket configuration that we would use. This is based on either Genoa or Turin-based AMD CPUs. Obviously, with DDR5 memory in here, it's so much more expensive. And honestly, it's like, the prices we're putting in here is like prices I see that you can source at. It's unclear, like, how deep does that supply run? And like, if you were to do this at really, really large scale, like you might even be paying more than, just like sort of the retail prices we're seeing, because, maybe they only have 100 DIMMs at that price, and then it's going to go up another $100. Definitely be cautious. So the dual socket build this is obviously if you want X16 PCIe Gen 5. The single socket build will look like this. This would be based on PCIe Gen 5 X8 to each GPU. And this is like obviously a smaller motherboard. Maybe you've got some more efficiencies or flexibilities around the memory as well. This is a good summary, I think, of like, if you're to go the route where you're building your own GPU server. The next thing that I want to do, and sorry, I'll preface that with, this is useful if, you want to build consumer grade GPU servers. I'll preface this with, like, if you're going for enterprise cards, you've got other options, right? Like if they're a standard, PCIe full height, double width, full length card, you can actually buy Barebones chassis that are, half the size of the chassis behind me here, that you can just slot the cards into. And like ASRock will sell those, SuperMicro will sell those. There's so many more options if you're going for the standardized enterprise form factor. I'll finish this by showing you how to actually assemble a server or a chassis like this. So like, what does the inside look like? Where is everything getting plugged in? And hopefully that gives you like a better idea of, how to set something like this up. And you just have to remember, like, this would be, if you're doing something with 5090s, 4090s, you're going to need something that's custom like this. Whereas if you're going for the standardized form factors, there's sort of a lot more like manufactured options out there. So this is the inside of the chassis. You can see the ASRock motherboard is there. I've obviously taken all the memory out of this, but the way that this all connects is through SlimSAS. So you can see that there's the GPU risers. There's 2 layers of GPUs in this chassis. So you'll put 4 on the bottom layer, 4 on the top layer, and you connect all that back to the motherboard, where basically each riser is going to have, 2 SlimSAS ports connected on the motherboard. And then in the BIOS, what you're doing is you're setting that to x16 so that that slot there acts as, like a dedicated PCIe Gen 4 x16 slot. The add-in NIC, it's the exact same idea, right? Like we have a riser here, and there's a NIC inside it, and then there's this SlimSAS cable here that's cabled back to the board. And because we're just using one, and there's actually one there, we've got that one set at x8. The storage, it's the U.2 backplane is actually underneath the motherboard, but we use these 2 SlimSAS ports here. They are set to x4, and they go underneath the motherboard to connect to the U.2 backplane, which is here. So you might be able to see, like, there's no way that's going to be any good, but at the back of each U.2 slot, you've got a a port that you're connecting your U.2 drives to. So that's the, I guess where everything sort of connects inside the motherboard. The assembly of these is super finicky just because of the layers of GPUs, but for power, once you've got the GPU in the slot there, you can just use one of these 600 watt cables, plug it into the top of the GPU, and you're good to go. So quite convenient. That was our solution. The PDB, it was kind of hard to see in the chassis, but it hosts up to 5 power supplies. So this is just a blank here. You could actually have another 1600 watt power supply in here. And these all work together in parallel to provide power to the whole system. So that's power to the motherboard and the CPUs, like all the memory, and then the GPUs eat up the bulk of it. So having this redundant PDB here, feeding those 600 watt cables is just such a simplification over, you see people using just a whole bunch of daisy chained ATX power supplies that aren't really working together. They're just sort of independent things all wired up. You can kind of see the bottom there. I apologize how messy this one is, but at the bottom there, you can see, the PDB, and that's what those power supplies are connected into. And that's where all the power for the whole system comes from. So I'm just trying to think right now if there's anything else in here that would be interesting, but I think this is enough to give anyone who's considering this an idea of how it all fits together. The concept is exactly the same. So if you use the PCIe Gen 5 motherboard, it's going to be the exact same sort of look and feel. You'll be using MCIO cables instead of SlimSAS cables. You'll be using a PDB that, this just uses ATX power. The Genoa motherboard that I used to use used a special thing. So yeah, I think that's really everything you need to know about the chassis. You can see here, I've actually got these shitty little PCIe Gen 4 risers. I do know these threw a bit of AER errors. This was sort of before we switched entirely to C-Pane. I was, trying out a bunch of stuff, but the concept is solid. And then there's the chassis, the 7U chassis, which I don't have one here, where the layout is actually we have a layer of GPUs here, as well as a layer of GPUs here, and we're able to shrink the size because, we don't need to stack the GPUs vertically on top of each other. Cool. So I'll end that there and then jump back onto my computer. Okay, so at this point, I think you should have a pretty good understanding of what is sort of the unit size that you build with, and that's an 8x server, and that's 8x of any GPU. Whether you're building the servers or you're buying the servers, they're going to come in that form factor. And so for us, we were doing 4090 servers. They pulled about 4.5 kilowatts each. We gave each of them about 6.5 kilowatts of available power. And what did that look like in a rack and then ultimately like in the facility, what we would do is we'd put 4 of those 10U servers, and say we were using 7U servers, we'd still only put 4 into the rack, and then we'd blank all of the empty spaces in the rack to contain, air and make sure that, hot air is going into one aisle and we can control that cold air is going into another aisle. For racks, like, depending whether you're building your facility or you're renting a facility, like they're going to kind of come in all shapes and sizes. Just like a bit of a history lesson, like a 10 kilowatt rack, 10 years ago was considered fairly power dense. Now we're looking at like 20 kilowatt rack is sort of just the most basic thing that you can do when you're talking about GPU infrastructure. For, like the big clusters, like the H200s, the B200s, like, each one of those servers needs almost 15 kilowatts of power provisioned to it. So, you're looking at like 40 kilowatt racks. And the way that they achieve that with air cooling is they're actually attaching it's called a rear door heat exchanger to the rack. So one of the doors on the rack is like actually almost like an air handler where there's like cold water going through it, and you're cooling the air that's coming out of the servers before it actually goes into your data center's cooling system. And that allows you to get densities like 40 kilowatts in a single rack. For cost efficiency, liquid cooling is going to just absolutely be the most expensive thing. But it's required for the high-end stuff, right? Like if you're spending $450K on B200 servers and they're liquid cooled and you're buying 1,000 of them, like, I think the efficiency at scale that you get from that, being able to have it more dense, like that's all worth it. If you're talking about building 5090 servers, you want to target 20 kilowatt racks. That's where you're still going to be able to air cool everything. The facility isn't going to need anything fancy like rear door heat exchangers. You're just going to leverage stuff like hot aisle and cold aisle containment to sort of maximize the amount of cooling that you can squeeze out of your air conditioners. So a 20 kilowatt rack, like what does that mean? For us, we'd have 30 amp power outlets essentially that were running at 208 volts. And we would take 4 of those and run them into the rack. So each one of those outlets, 30 amps at 208 volts, is about 6 kilowatts, just a little over 6 kilowatts. And we would take 4 of those and run them to the rack. So we've got like 24 or 25 kilowatts of power to work with in our rack. And what we would do is, because each 4090 server was taking just under 5 kilowatts each, we take 4 of those and we'd saturate the amount of power in the rack up to about 80%. So the numbers worked out like almost perfectly. The 10U chassis meant that like we didn't need to blank any of the empty spaces, and we were left in a 42U rack with 2U at the top where we could actually put switches. So we put a pair of switches in each pod that every server connected to. Every server would connect to each switch. So if any one of those things failed, you'd still have the full 10 gig connectivity throughout the whole pod. That's, like the theory, right? So like that's one rack. It's got 4 PDUs, it's got 4 servers, and 2 switches or 0 switches. And then what we would do is we'd build pods with those racks. So you could take, I think it worked best, we would do either 8 or 16 racks in a pod. And I think the 16 rack pod, it just required more cooling around it, so it was harder to contain. But if you just do 8 rack pods, you're looking at like 4 racks on one side, 4 racks on the other side. They're loaded up, all exactly the same. And we were doing hot aisle containment where the backs of all of the racks were blowing into that hot aisle, and we would trap all that hot air in there and had like almost like a chimney on it where we would either vent that chimney through the air conditioning. So, you just run it straight into the air handlers. So you've got hot air going over the air conditioning, which means that you're getting, the most cooling out of those air conditioners. Or if we wanted to do free cooling, we had exhaust vents around the facility where we could really just sort of use the chimney to move all that hot air up to the roof of the facility. We're in a fairly tall building, and the exhaust fans that we had running up there were able to move enough hot air out to actually just cool everything down. Another important thing to remember is that if you are exhausting air out of a building, you need to be intaking it at the same pace. Otherwise, you're gonna end up with negative pressures, and you're still just sucking air in from all kinds of different places. So you wanna make sure that you're filtering air as it comes in, because if you're just bringing fresh air in from outside, the amount of debris that you accumulate over time is insane, and then that all builds up on your systems. first things first, figure out what your rack scale infrastructure looks like, your building block. From there, figure out like, okay, what sort of containment and what sort of like pod do I want to create? That's sort of a network decision. That's like a cooling decision, just physical space decision. And then from there, you want to figure out like, okay, from a facility perspective, like, let's say we have 500 kilowatts of IT load running across all these different pods. How much heat do we need to eject? How much air conditioning do we need to bring in? How do we ensure that the coldest air we have is, going into the servers, and the hottest air we have is obviously nowhere near that cold air, and it's going to be either ejected or cooled down. Yeah, it's important if you want a scalable data center to, obviously focus on something that you can continue to grow and you can continue to cut and paste. So yeah, you have to get it up to that rack scale capability. And then in terms of cost efficiency, like, going beyond that 20 kilowatt mark, it just means that, you either have to get really, really good with the containment or start to add in expensive infrastructure. The next thing that I want to talk about is around the operating system and testing this, the systems when you build them. Most of the GPU cloud business that exists right now, it runs on Ubuntu server. So Ubuntu server 22, 24, and 25 with, NVIDIA drivers. There's a million different drivers and a million different ways to install them. You need a system that basically lets you very easily deploy something like Ubuntu server, something that automates your driver installations and all of the different configurations that you have, and then a testing process that you follow. So we had a stress test actually from CPAN Risers. So he has a utility that if you buy his risers, he'll give you access to. It stress tests all of the PCIe links. It makes sure that the bandwidth between the GPUs is, what's expected. And then you run it over time and you see if any AER errors accumulate. We relied on that tool super heavily. Like every server we ever built, we would, test it for 48 hours to a week. If you catch any errors in a 48-hour window, like over a multi-year window, you're bound to have like serious problems. So super useful in checking that, the signal integrity to each of the cards are good, checking that the thermals to the cards are good. Something you need to look out for is thermal throttling. So if you're running a stress test on your system and you see that, okay, it's 4090, it should be drawing 450 watts. It draws 450 watts for 30 seconds. The fan's at 100%. The temperature keeps climbing. And then all of a sudden, the card just starts drawing like 230 watts. That's thermal throttling. That's the GPU intentionally slowing itself down and drawing less power because its cooling mechanisms aren't sufficing. It's going to overheat if it continues to operate at full capacity. So it throttles itself down. It's really important you identify this kind of thing because that leads to GPUs crashing if they overheat, as well as in systems where all of the GPUs need to work together, one GPU going slow will actually throttle the entire server back. So you'll have 7 other GPUs that might be totally fine. They can't operate at full speed because, somewhere in like the neural net, all the layers loaded into that one slower GPU, they're all going to be dependent on that finishing for them to proceed. So very important that you test your systems. You can do it with just a simple PCIe stress test or the GPU stress test. You can deploy it on Ubuntu directly. You can deploy it in Docker, but you absolutely need to build up a system for this while you're building your servers, because it's really easy when the server's sitting there on the bench to, okay, like this one's getting really bad AER errors, like maybe the cable's bent, maybe the cable's not plugged in all the way. Like there's all these things that you can get quickly. Once it's deployed into a pod, into a rack, it might be with a customer, like taking it out, scheduling that maintenance, figuring out the issue, like it just adds a lot of complexity. So you absolutely need to get all this stuff done up front. So that's what I've got for building your own infrastructure. Obviously, you can save a lot of money by just doing everything yourself from scratch. And you save the most money if you're doing consumer GPUs. The reason that people go with 5090s right now is they have the same performance really as an RTX Pro 6000. They obviously have less VRAM, but if it's something to do with a model where, 8 5090s has enough VRAM to support the model, you're getting insane value out of a system like that. So the rental market for them is really, really healthy for inference. The, cost to build them is obviously way lower than the enterprise stuff, but you run the issue of you need to do it yourself. There is vendors out there that will sell you pre-built 5090 servers. I can't really speak for how good of a deal it is. I remember every time I would check, it was always like, thousands of dollars more expensive than I knew it would cost me to build it. So I never went for it. But I think a good example that I'll just give a shout out to is Octa Server. I know they have a very good 5090 node that you can buy. And there's another company actually called TinyBox. It's part of Tiny Corp, which I don't know if you've heard of, but they do a lot of really cool stuff. And they have another really good sort of like retail 5090 node that you can buy. So those are your options there. If you are going with the enterprise cards, like I said earlier a few times, you can go with Barebones chassis. ASRock makes them, SuperMicro makes them, everybody makes the Gigabyte, ASUS, one chassis will even do it for you. And what a Barebones chassis is it's a GPU server with no components in it. So it doesn't have CPUs, doesn't have memory, doesn't have storage, but it's like all of this sort of complexity and cabling and all the things that I sort of went through today sort of baked into like either a 4U or a 5U box. And then what you do is you buy your GPUs, like your RTX Pro 6000s, you put 8 of them in, maybe you've got a PCIe switch in there and you can put 10 of them in, you put your CPUs in and you're good to go. You can get really good deals on these. So like if you think about something like an RTX Pro 6000 where you might be spending 10 grand on every card, like you're in for 80K right there. And then, this Barebones chassis might only cost another 10K just to not have to worry about getting the motherboard, getting the risers, maybe a PCIe switch. Like all of these things would add up where sure, you're saving a couple $1,000 building it yourself. But if the server costs close to 100 grand, saving a couple $1,000, it's not as big a value as you think it is. That's what I would say about Barebones chassis. When you're buying Barebones chassis, ensure it's spec'd for the CPUs you want, make sure it's spec'd for the GPUs you want. Like the power connectors are a consideration, the cooling capability of it is a consideration. So make sure all of that is totally in line before you buy one of these. And then I'd say especially in the used market, like if you go on eBay, you'll see these available. There would be a lot of retrofitting required right now to take one of those that you're seeing on eBay to use with something like an RTX Pro 6000, because RTX Pro 6000s need 600 watts of power and cooling. And whatever these decommissioned things that are being sold on eBay, like they're probably expecting 300 watt cards. So you can't just like go and stick a 600 watt card in a slot that only is, ready for 300 watts of draw. Definitely worth considering. I think there's definitely opportunity like repurposing old L40Ss and sort of the older gen stuff, getting into these chassis. You just have to know what you're doing when you're doing that. So the high end, let's talk about SXM based servers. If you're not familiar, there's sort of two form factors that GPUs have. There's like the PCIe form factor, which I think everybody can picture in their head at this point. And those go in PCIe slots. They're, on the PCIe bus, super straightforward. And then there's backplane based GPUs. So with NVIDIA, it's called SXM. With Intel and AMD, they call it OAM. And what these are a special sort of 8-card backplane that sits in the chassis and has super, super fast interconnects on its backplane. So all 8 of those GPUs are able to basically, NVIDIA manufactures the board, it places the GPUs on there, it places the PCIe switches on that backplane and allows interconnects at insane bandwidths between the GPUs. And then they ship those backplanes to the OEMs, and those OEMs build a server around it. And because like of the amount of bandwidth that goes into these things, because of the amount of, NICs that need to go in these servers, like when you hear about like a B200 cluster, an H200 cluster, like those have 200 gig and 400 gig NICs, and like 8 of those all in the chassis, connected to InfiniBand switches and interconnecting all of the nodes at like huge bandwidth. There's sort of a huge amount of complexity there, and you can't build those servers on your own. I have seen like you can find SXM backplanes for sale for like older generation stuff. I have never tried to buy an SXM backplane, like say for an A100 or something like that, and then try to figure out how to get that connected up to a board. Not to say it's impossible. I've never tried to do it, and I've never seen the value in trying to circumvent this end of the market. So with those nodes, like I think they are a very good investment. And I think if you're very well capitalized, that is the way to go. If I were to get back into this business, I would probably try to play that game rather than dealing with hundreds of 5090 nodes. I think the value that you can create for yourself here is just understanding that there aren't really alternatives. NVIDIA controls most of the market. They manufacture the GPU, they manufacture the backplane. The OEMs need to buy those things at like huge cost. When the manufacturer goes and, builds a server and gives you the quote, like they're making money, but they're not like making that much money. Okay. Like it's like in a lot of cases, low 10% margins. And there's sort of tiers to it, but I think all of the benefit that you can gain here is just understanding what you need and shopping it, and making the vendors be competitive with each other. And if you can get to a point where like you're pretty sure like, they're making like 8% margin or something on the deal to you, like trying to build that shit yourself is like, you're not saving really anything. The way that the vendors work is you're going to have like tier one vendors like Dell, Lenovo, HPE, Cisco. There might be like a couple other big like enterprise IT providers. And those are going to be the most expensive options that you see because, they're selling to like the Fortune 500 crowd. Like these are big companies that need to buy IT equipment and have been buying billions of dollars of IT equipment forever. And they need to know that it's stable. They need to know it works. A lot of these servers come with like a 4-hour parts warranty globally, where if like something breaks, like they're going to have the replacement there in 4 hours. It's a different class of infrastructure that if you're just like an individual buying it to like run it and rent it to people, you're probably not going to see value in a lot of that stuff. So when you get the quote from Dell and you're like, holy shit, like why is your thing 50K more expensive than, the Gigabyte option? That is why. But because of that, and because those vendors have like a brand, the resale on those nodes is obviously a lot better than in the lower tier vendors. So the one that's probably surprising to people is SuperMicro. I would say it could be considered a tier one vendor in terms of AI infrastructure. They obviously sell a ton of GPU servers, but they are, in the most part, like in the most cases, they've been the cheap, server provider in comparison for the last 2 decades. Like I worked at Dell selling like, enterprise storage and enterprise, private cloud stuff. You never came across SuperMicro. And when you did, it was like, okay, well, we don't really care that that's cheaper. This is a different outcome that you're buying. SuperMicro participates here. I know with AI servers, like they have like a, really, really strong market share. I think a lot of that is because they just sell the hardware. They just get the GPUs from NVIDIA, wrap their sheet metal and motherboard around it, and they're willing to do deals at low margin. They will have strong resale value because they have a good brand. But then with them, you've got vendors like ASUS, Gigabyte, ASRock. Those are all like, semi-well-known brands that also do the same thing. They'll buy the GPUs from NVIDIA. They'll wrap a server around it. You'll have a warranty on it. So if something breaks, like they'll fix it. They're large global companies with like the support, to ensure that stuff moves as you'd expect. Like if you buy it, you're covered. Another one that I'd add to that list that I don't see there is Quanta. They also do fairly large scale infrastructure. Tier 3. So this is where you can actually save most of the money. These are, new manufacturers that don't have a huge brand. Like I keep talking about one chassis, like they sell me just the Barebones chassis. They sell me just the sheet metal. Like you can work with them and only buy what you need. They are manufacturing companies. And so like they're doing their margin at manufacturing rates, and you can save a lot of money, right? Like if you look at an Averiz H200 or B200 server, and then you go and look at a quote from Dell for the same thing, you're going to get a huge cost savings against the Dell node. The challenge you're going to run into is the depreciation schedule and the resale value. I would challenge that after 3 to 5 years of running your Dell node, when you go and sell it, everyone's going to know what that is, and they're going to be down to buy it from you. The Averiz one, you are probably going to have a harder time going about that. You might actually have to take it apart, and you'll be one of those guys selling an SXM backplane. That's how that market works. The way that you maximize your value here is you need to get a quote from as many of them as you can, as close to the source as you can. There is such a large number of players out there that are basically just running around as resellers of resellers of resellers. Like I think like if you're planning on doing this at some kind of scale, get an account with Dell, get an account with HP, like open one with 8 of these vendors and do the legwork to ask all of them, like what's your inventory? Like, when are you getting your next shipment of NVIDIA GPUs? Like what are the pricings? Get the details really solid, because if you play that reseller game and it's like a reseller to a reseller who's then working with like Dell to get you your quote, so many things can go wrong along there, and so many different, exaggerations or sort of like missed deadlines. Like all of those things start to compound. And you end up in situations like this has happened to me, where even just buying GPUs, I bought it from one guy who was buying it from another guy who was buying it from PNY. And it's like, the one guy is saying, oh, well, like PNY isn't shipping them. And then he's telling his guy, and then it all bubbles down to you, and you're like, okay, well, I'm absolutely hopeless here. Like, I just have to wait until, somebody starts telling me what's actually going on. I would say, yeah, open accounts with the vendors that you see the value in. Your biggest point of leverage is the competitive quote. And then the way that it works is each of these companies is going to assign you a sales team. Depending on how much money you're spending with the company, like you'll get sort of higher and higher level teams. But basically what you need to do is be able to arm your sales team with the stuff that they need to go and get you the discount. So like at Dell, our vested interest is like, we want the business, like we want the revenue, we're paid on revenue. So we're like on the customer's team to bring the deal in. And so if they come to us and they say, hey, like, the Dell quote was $1 million, but SuperMicro gave us a quote for $750K. So like if you have an account with Dell, like you'll have your Dell guy, and like this will be your Dell sales guy. We like Dell, we'd rather have Dell. Like, can you guys match the SuperMicro quote? Like now we have ammo that we can use to go and actually request the discounting that we need. We have a case to make because Dell like wants to be competitive. They don't want their competitors winning. The more reasons that you can give, the account teams at these companies to go and get the discounting, the better outcome you're going to get, where, they can go into the war room and ask the VP if we can do the deal at 5% margin because we want to fuck over HP, right? Like that is sort of the level you want to get to. And that's how you just ensure that you're getting stuff at prices where it just doesn't make sense for you to build. If you can be buying this enterprise gear at almost the cost to manufacture it from like a tier 1 vendor, you're going to be doing really, really well with it, right? That's the levers that I'd pull on when it comes to buying. You want to make sure that you look at lead times. So the way this works is obviously the GPUs come from NVIDIA. They're going to give the manufacturer the lead time. So like right now, for instance, like somebody told me ASRock has 32 B200 backplanes coming in June, and ASRock is selling that cluster of 32 B200s for just over $400K a node in July is when they want to deliver. So they're receiving it in June. They'll have them manufactured by July. They want to be shipping in July. And like, they have the price that they want. The reseller community is like gobbling that up and going out trying to sell it to people. But you want to just like have a very strong understanding of like what is the situation? When are the backplanes coming? Like, am I buying into an actual delivery or am I just entering the backlog? Credit. So, in the IT world, like you could typically get like net 30 accounts fairly easily. With GPUs, a lot of vendors just require upfront payment. They'll require deposits and then pay on ship. There's varying levels of this, but just know that if someone is giving you net 30 or like net 90 or something like that, that costs money to do. And so you're receiving a lot of value there, and that might be something that you're actually paying for, that you don't even really realize like how much cost that's actually adding to what you're doing. When it came to equipment financing, like I know at Dell, like we had models where you could like pay for what you use or like lease the equipment. This all was basically like it's a glorified lease, and it was done by like the financial company within Dell, and they would finance things at like, I think like anywhere from like 8% on the very low end to like 20% on the high end. Like when people are presenting these like very sort of attractive models and saying like, oh, like you're saving money because XYZ, you just need to understand that you're just borrowing money and you're paying a certain cost of capital on that money, which might be something that you want, but you do need to understand that you like the money doesn't just come from nowhere. If you're working with a financial services business, like they have a margin that they need to hit. That's how credit works. The final point that I'll leave this with, which is probably like the most exciting part of this, and one of the reasons why I'm like considering getting back into the business, is there's a huge tax incentive around buying, IT infrastructure as well as GPU infrastructure. In the US and Canada, you can write off 100% of your GPU server in the year that you buy it. There's actually a lot of like private equity and high net worth individuals that are, have super high incomes and are basically just spending huge amounts of their incomes and their profits to reduce their tax liability. And the way that you can look at this is like if, like, let's say you're in Canada and you're making say $2 million a year or something like that, like you're paying like over 50% in tax if you don't find a way to reduce that income. And so going and buying 4 B200 nodes or something like that, where the assets will retain their value, relatively speaking, they'll generate income for you over the next couple of years and sort of defer the tax liability. It's like actually a very, very strong investment vehicle where it almost feels like you're buying the infrastructure at like 50% off, and then you're receiving like the full benefit of renting to people. So a huge reason why people put their money into this, and this might be a good way for people to find investors if that's what they're looking looking for is it's 100% tax write-off. So anyone with income that wants to offset their income can buy one of these, offset the income like 100% against the purchase, and then they've got this asset that is just going to generate them money on an ongoing basis. This was like obviously the longest video I've ever done. I did just sit down, I had notes, but I did just sit down and I just started talking. I hope that this was like the amount of detail that people need to like dig into, I don't know, like every aspect of this. Like obviously, like, you know, you can go much farther into this. Like I have screwed around with those motherboards for hundreds of hours, and I'm still probably not totally an expert on the whole thing, but this should give people at least a very good head start and a good reason why, I don't know, I'm sort of saying the things that I'm saying. So if you enjoyed this, and actually if you made it to the end of this, very impressed, but yeah, I do appreciate it, and look out for the next videos. So, you know, it's going to be a 6-part series. I've got the first one here, which is about the servers, like building them, buying them, getting your infrastructure. The next one that I'm going to do is going to be about the facility. Like, you know, what do you put this stuff in? Like once you get it, what are the things that you should spend your money on? And you know, what can you save money on depending on what you're doing, right? Like if you've got 50, 90 servers, you don't need to go all the way with the data center. But if you're buying B200s for $400,000 a piece, like you should probably get the right facility for it. Anyways, I'm going to stop talking. Thank you so much for watching, and I'll see you on the next one.